For years, the question was relatively simple. Is this assembly clean enough? Today, that question has changed. It's now clean enough for what? I'll answer that in just a moment. Stick around.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
Welcome, or hopefully welcome back to Reliability Matters. I'm so glad you're here. This is part 2 of our series on post-reflow cleaning. In part 1, we looked at how the industry transitioned from a clean everything approach to one where cleaning became optional. That shift was driven by environmental regulation, enabled by no-clean chemistry, and supported by the design characteristics of assembly at the time. But as we discussed in part 1, the conditions that made no-clean viable have changed. So today we're going to bring that discussion into the present and explore what cleanliness really means in modern electronic manufacturing. For many years, the industry relied on a simple definition of cleanliness. If the ionic contamination level was below a fixed limit, the assembly was considered clean. That limit, based on resistivity of solvent extract or ROSE testing, historically was 10 micrograms of sodium chloride equivalent per square inch, or 1.56 per centimeter squared. That was simple, but it was also flawed. That limit was established decades ago in a very different era, an era with larger components, wider spacing, and far less demanding environments. As assemblies evolved, that definition of cleanliness became increasingly disconnected from real-world reliability. With the introduction of updated IPC requirements, particularly in the current IPC J standard 001J, the industry moved away from fixed cleanliness limits. Instead, the question became whether a specific assembly could tolerate the level of contamination present without failure. That's fundamentally different from the former subjective approach. Today's approach is objective. Rather than relying on a universal number, manufacturers are now expected to generate objective evidence that their process produces reliable assemblies. That evidence typically comes from surface insulation resistance, or SIR testing. SIR testing subjects assemblies to elevated temperature, high humidity, and electrical bias. These are the exact conditions required to activate electrochemical migration. If the assembly maintains high insulation resistance, greater than 1 times 10 to the 8th, under those conditions, it is considered reliable. This shift reflects a deeper realization. Cleanliness is not a number. It's a function of risk. But SIR testing alone is not sufficient because it is typically performed on test coupons rather than actual production assemblies. That introduces the need for process monitoring. Using ionic contamination testing, typically through ROSE testing, manufacturers establish an upper control limit based on assemblies that have already passed SIR testing. Production assemblies are then tested periodically to ensure contamination levels remain below that threshold. This transforms cleanliness from a one-time validation to a continually monitored process. Now let's revisit no-clean flux. When the industry adopted no-clean, there was an implied contract. The assumption was that the residues left behind would be both invisible and benign, but that assumption was based on the designs of the time, through-hole components, large spacing, and high standoff heights, assemblies that were far more tolerant of residues than what we see today. That contract held for a while, but today that contract is under pressure. Modern assemblies are smaller, denser, and far less tolerant of contamination. And just as important, they are now operating in environments that were never part of the original equation. Not just external environments, but internal ones. One of the most overlooked reliability risks today is the formation of localized harsh environments inside the device itself. Poor thermal management, enclosure design, and trapped moisture can lead to internal condensation within the assembly's enclosure. During thermal cycling, particularly during power down events, temperatures inside the device can fall too quickly, with temperatures dropping below the dew point, causing condensation to form directly on the circuit assembly. Now combine that with ionic contamination. You now have moisture, residues, and electrical bias, the exact conditions required for electrochemical migration. This is why failures are often intermittent, delayed, and difficult to reproduce, because the environment that triggers them is not always external. In many cases, it's created by the device itself. Now let's come back to cleaning, because the method matters just as much as the decision to clean. Historically, when the industry cleaned circuit assemblies, the dominant process was immersion-based vapor degreasing using CFC-based solvents. These systems relied on the principle of condensation. The solvent vapor would condense on the cooler assembly, dissolve contaminants, and then drip away, carrying residues with it. It was a highly effective process for the assemblies of that era. But those assemblies were very different. They were primarily through-hole with large gaps and high standoff heights. The solvent could easily reach most surfaces, and the physics of condensation-based cleaning worked well in those relatively open geometries. Let's fast forward to today. Modern assemblies feature low standoff components, tight spacing, and densely populated boards. The areas that require cleaning are often located beneath components, not just on exposed surfaces. And that changes everything. Immersion and condensation-based cleaning processes rely on fluid access. If the cleaning medium cannot reach the contamination, it can't remove it, which is why modern cleaning has increasingly shifted towards spray and air technologies. These systems rely on mechanical energy, impingement, and fluid dynamics to force cleaning chemistry into tight spaces and dislodge and solubilize components. And here's the key point. In modern assemblies, cleaning is not just about chemistry, it's about delivery. It's about whether the cleaning process can physically access the contamination. Under low standoff components, the available space is extremely limited. Frequently, only very fine fluid particles can penetrate beneath these components. Larger, high-impact streams may deliver force, but they often can't reach where the residues actually are. This is why diffuse spray patterns, which produce smaller fluid particles and broader coverage, are more effective in modern assemblies than concentrated, coherent systems. They provide better penetration into tight geometries and more uniform cleaning across the entire assembly. And this ties directly back to reliability. If residues remain trapped beneath components, they remain available to participate in electrochemical processes when moisture and electrical bias are present. Now, add process variation to the equation. It's not uncommon for peak reflow temperatures to drift slightly below recommended values during the reflow process. These changes may not affect solder joint appearance, but they do affect flux chemistry. Incomplete flux activation and encapsulation leads to increased ionic residues, often concentrated beneath low standoff components, exactly where they are most challenging to remove. Controlled studies have shown that even small reductions in peak reflow temperature can result in increased contamination and reduced SIR performance. So while the assembly may look acceptable, its reliability margin may be reduced. Electrochemical migration is often cited as the primary reason for cleaning, but it's not the only one. Cleaning improves conformal coating adhesion by ensuring proper surface preparation. It reduces corrosion risk by removing chemically active residues. It helps prevent signal integrity issues caused by contamination and charge trapping. It improves cosmetic appearance, which influences customer perception. And it increases process robustness, making the manufacturing process more tolerant to variation. There's also a broader shift in expectations. Historically, IPC Class 1 products were considered lower reliability. But today, even those products are expected to perform in environments that include moisture, contamination, and temperature variation. Wearables, IoT devices, and consumer electronics are routinely exposed to conditions once associated with higher reliability classifications. The classification has not changed, but the expectations have. And that creates a gap between how products are built and how they're actually used. So what does all this mean? It means cleaning is no longer just a process decision. It's a reliability decision. It must be based on design, environment, process capability, and objective data. If your process is validated, controlled, and proven reliable without cleaning, then a no-clean approach may be appropriate. But if there is uncertainty, variation, or exposure to harsh environments, whether externally or internally generated, cleaning becomes a critical control step. In Part 1, we explored how the industry moved away from cleaning. In Part 2, we've explored why many are moving back. Not because no clean failed, but because the assumptions behind it have changed. Assemblies are smaller, environments are harsher, expectations are higher, and the cleaning process itself must evolve to keep up. So the question is no longer, is this assembly clean enough? The question is, clean enough for what? Now, that's a wrap on another episode of Reliability Matters. Be sure to subscribe to the podcast so you don't miss an episode. A huge thanks to PCB Chat from the Printed Circuit Engineering Association at PCBchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Got a question or an idea for a future episode? We'd love to hear from you. Just visit reliabilitymatterspodcast.com. Thank you so much for being here. Until next time, keep learning, keep doing it right, and remember, reliability matters. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.